And we are currently moving on to the next presentation. We had a small change, namely the person who will be presenting have been changed from Ewa Klejman to Karol Masztales from the same group. So don't worry, the same topic will be covered. And he will be talking about the sampling air using the stratospheric balloons.
Yes, I will be sharing my screen in a second, if I may.
Perfect.
And
yes,
as you said,
may
our
and
topic,
you should.
And our topic will be, as you mentioned, sampling the stratosphere using a device we've developed. All right. Please do let me know if it is visible.
It is visible, and I will let you know 6 minutes before the deadline for your designated end of designated time.
Yes. Thank you very much. All right. In that case, I will invite my colleague Ewa Klejman to start our presentation. Ewa, please start our slides. Is Ewa here? Well, apparently we've lost Ewa. All right. In this case, I am going to cover for Ewa. Please excuse us, but I think her internet just went down. All right. So, as I mentioned, our topic is stratospheric research. We're a team of students from the university.
Sorry, I'm back.
All right. Well, then, Ewa, take over for the first slide, please.
Yeah, so sorry for the problem. I'm just moving, and it's kind of hard. Okay. So, dear delegates, distinguished guests, it's a well-known fact that microplastic is a threat to the environment, as a pollutant is present almost everywhere. Together with my team, we are honored to present you our research project, SamplAir Atmospheric Sensing of Air Pollution. Today I'm going to present together with my team, Filip Bąk.
Good evening.
Jędrzej Drozdowski.
Good afternoon.
And Karol Masztales.
Well, good afternoon.
Let's start from the beginning.
So the aim of our project was to design a rover, to design a device intended to collect environmental samples from planetary atmospheres, namely the Earth's atmosphere, at various altitudes. The idea was to collect samples of things like microplastics and other pollutants at various altitudes, and then bring those samples back to Earth and analyze them in the lab. A secondary goal of our project was to also conduct science popularization, because we believe that microplastic is a big issue that needs to be discussed widely. The goals we had when designing our probe were efficiency, minimization of the cost so that the probes can be produced at wide scale, and optimization of the working of the device. For the purpose of the project, I think Ewa can tell us a little bit more about that.
We believe that the project we created touches the important topic of the environment. The more developed as a mankind we become, the more opportunities to protect the environment we get. Investigating the topic of microplastic pollution provides a new perspective on the environmental pollution overall. However, we are not limiting ourselves to the microplastic research only.
Yes, in fact, our research covers a couple of areas. As my fellow speaker Ewa mentioned, it's microplastic, but also we research smog, PM2 and PM10 particles, and aerosols. So we're looking for emissions from various sources. These can include volcanic ashes. We can also research pollution emissions from households or industrialized and urbanized areas. So our device is very unique in the sense that it can work in pretty much any environment and gather samples from various sources. Regarding on how our device operates and how it was constructed, I think our colleague Filip can tell us a little bit more about that.
We have created our device from ground up. Most of the elements have been created using FDM 3D printing technology. We use a PLA filament, which is biodegradable, light, cheap, and durable. The most time-consuming process was designing the whole device and assembling it. Besides the 3D printed mechanical elements, our probe has two electric motors, a vacuum turbine motor and sample selectors motor. The systems are powered using 12 volts lithium-ion battery pack integrated with casing. A crucial factor in the design process was the structural integrity and air tightness of sample selector mechanism, which secures all samples from outer environmental factors. Another task was the design, manufacture, and disassemble the printed circuit board of our probe. The final task was to develop software, which my colleague Jędrzej will describe in more detail.
The main difference between previous and current version of our project from the hardware standpoint is the onboard computer. Previously, it was Arduino, which is not so powerful board with microcontroller, and now it is a fully fledged computer, a Raspberry Pi. This change allowed us to use more sensors over different interfaces like USB or I2C, but it also forced us to create completely new software. A process of collecting data and samples from a software standpoint is fairly simple but also robust. During the whole flight, a computer collects data from sensors such as thermometer, magnetometer, barometer, etc., and stores it in a database for a further analysis, but it also sends it to a radio transmitter. The second thing that we transmit are photographs from onboard camera, but using other transmission method called SSTV. We also have two cameras that are separate from device's system that are constantly recording a video. Other crucial aspect of the flight is a localization of the probe. We retrieve the samples after a successful flight, as this is the main goal of the mission, and the current altitude of the device is also necessary for the proper functioning of the probe, as it is designed to collect samples at certain altitude ranges, for example, 5 to 10 kilometers, 10 to 15 kilometers, etc.
Right, and regarding the mechanical design of our device, I will let Philip tell us a little bit more about that.
So our device operates somewhat like a vacuum cleaner with many filters. The probe with the mechanism is lifted into the air using a balloon, reaching heights up to 40 kilometers above the sea level. During the flight, onboard sensors monitor plenty of environmental parameters, and our sampling mechanism collects individual samples of particulates suspended in the air. The mechanism is mainly based on vacuum turbine and sample selector. After the probe reaches its intended burst altitude, the descent and landing procedure is initiated. A parachutes get deployed and samples are returned safely back to Earth. After landing, the device is secured and collected to bring the samples to the laboratory for further analysis.
Right, and regarding the analysis and the research we're doing on samples, I think Ewa can tell us a little bit more about that. So Ewa, please.
After recovering the samples from the device, we proceed into the examination of the sample properties. Up to today, we have conducted a few initial tests, including scanning electron microscope. On the right side, you can see two pictures obtained from our samples. Both of them contain two foreign objects, which, as we have managed to establish, are not a part of filters or device itself. We are currently working on analyzing our samples. However, based on our flights and samples, we have drawn initial conclusions, which Karol will tell more us about.
So the initial conclusions we've done, we can split them into two categories. One of them is regarding the device itself, and the second one is about the samples. So regarding the device itself, we've conducted a flight test, which has proven that our device can operate in the stratosphere as intended. And it can also be safely recovered after landing. So it proves that our technique, our method works. During the iteration process, as we've already done two flights and I'm working on the third flight, coming up in a couple of weeks, we've done a lot of debugging on our device. So the initial one had a bit of software issues and other technical trouble, as it always happens with research projects. We've obviously improved on that with the second version, and now the third version has much smaller improvements, much more fine-tuned improvements, which should pretty much produce perfect, satisfactory results. We've also been working on lowering the cost of production compared to the research value that this device brings. So currently the device is low enough in cost of production that pretty much any university student team from any engineering department could make a similar device given the blueprints and the methods we described. We've also optimized and improved the device a little bit between the flights, changing the specifics of how the selecting mechanism works, how the turbine operates, and so on. But these are the details. And the initial conclusions from the research, I think Ewa mentioned those already. So, for example, we've detected those granules that you've seen on the scanning electron microscope images. So we are detecting something. We still need to conduct further research to determine what it is precisely and what the sources of the pollution are. And we would like to talk a little bit about applications of our device. And I think Ewa is the most suitable person to talk about these. So, Ewa, please take it away from here.
SamplAir is a unique device with a huge application potential. It provides a new perspective on environmental pollution. It allows us to monitor the pollution level in a diverse range of research areas. It gives us a chance to conduct an innovative research, allows us to regularly control the environment, and gives us accurate view on the air quality and precise information about the sources of the pollution. SamplAir has come a long way in order to be in the form it is right now. We want to share a little of its story and achievements.
Yes, before we move on to the story, I would just like to add one thing regarding the various environments our device is meant to operate in. We are actually currently developing a new version of the device intended to work in extreme environments, in environments that are acidic and high temperature. So we are trying to expand the range to also be able to sample aerosols from very extreme environments, the most extreme place on Earth. And now for a little bit of talking about the timeline of what we've been doing and how this work has been going on. So as a student group, we've started off with a very small grant from Ochota na Nauka. That's a program organized by the city of Warsaw. And I think that's a good starting point for a smaller students group. We've developed the first prototype of the device. We've developed the conceptualization of how to make such a device, how it should operate. And actually, we've managed to create a patent-pending design of the selector and the turbine mechanics. So the mechanism we use for sampling is already patent-pending. After that, we've started writing articles about it. So we've written a popular science article about how stratospheric balloons work. Our device has appeared in a couple of competitions. So, for example, it has scored a special award in one of the competitions in Poland for student inventions. We've presented it already at some conferences. I believe we've taken a prize at the International Conference of Young Researchers. We've done a seminar for the Astrobiology Society, which we're talking in front of today, but also many more distinguished guests, and we're very proud of that. I did skip that one, but we also received a second grant from Ochota na Nauka, which was for the development of the second current version of the device. Right now, we are approaching final stages of the National Explorer competition, and we are already in the regional stage, and we are approaching the national finals. And a little bit more about the future prospects, I believe, because that's something we're working on currently. Our device is made from pre-printable materials. So we've decided that we want to make it more environmentally friendly. Even though our material that we're using currently is biodegradable, we've also decided we want to make it recyclable. So right now we are working on developing a version that is using filament, free-printing filament, made from bottle caps. It proves a bit difficult in terms of the printing techniques, and it has a bit of changes to the design. But we believe that's a good step to also take for the environment. And I've mentioned this single future plan, but I think Ewa can tell us a little bit more about further future plans we also have for our flight. Ewa,
yeah,
please.
so as Karol mentioned, we are not planning to stop. We have a lot of plans in regard to this project, with main being a focus on improving its quality, experimenting with different filters and designs. Furthermore, we hope that we will keep collaborating with different institutions, organizations, and we are definitely not planning to stop popularizing science. Thank you for your attention. The project was financed thanks to the Ochota na Naukę and Miasto Stołeczne Warszawa. We also like to thank our patrons for supporting us and our work. If you have any questions, we will be happy to answer them.
Yes, if there are any questions, I will be taking them, and you may start now. I would just like to show the patronate and financing of our project, but besides that, I believe questions. The floor is open for questions.
Perfect. Thank you so much for this amazingly professional presentation of very, very interesting project and being amazingly on time. So congratulations for you. You are an amazing team. We don't have any questions yet, but if you have any, for example, applications for this device, please let us know or talk with the guys later on. In the meantime, I have a quick question. Have you already, in what kind of situations have you tested your device? And for example, how high were the samples collected and what did you find there?
I think I can start answering this question, and if our colleague Casper is here, he'll be able to add a bit more about the RTUs. But in general, we've taken 2 flights. The first one was in quite bad weather conditions when it was lightly showering with rain and it was quite cold. I think it was somewhere around October or November, if I remember correctly. and the second flight was quite sunny weather. So we've already tested it in, let's say, variable weather conditions. But that was more of nominal flight environments in the sense that we're flying just in normal atmosphere. We're not flying in any acidic environments or extremely hot temperatures and so on. So yeah, and regarding the altitudes, I am not certain of the exact altitudes, and I would like our colleague Casper to tell us about that. Casper, are you there?
I don't think I can see him.
I think he is there, but he is not as a presenter, so he cannot speak. All right, I'll just check.
Roughly. Don't worry. Just roughly.
I think it was about. I can tell you that it was above 25 kilometers. That's what I can tell you definitely.
Okay. Cool.
But the altitudes are just determined by the balloons we buy. So really, it's just a matter of financing and how much of a balloon we get. Because technically, stratospheric balloons can carry payloads up to like 50 kilometers. We think that 40 is the upper barrier for our technology, let's say, for our methodology. But that's the rough barrier we can have for flights in stratosphere.
Amazing. And what about the findings? So what you mentioned that you have used SEM to collect or to analyze the collected particles. What did you find there?
I think Eva can elaborate on that more specifically. I'll just go back to the slide for a second. So I don't think we have the exact specifics of what is on the SEM. We know it's pollution. We don't know the source yet. I reckon, but Eva will elaborate on them more.
Yeah, I can take it from here. So at this point, we are currently investigating the things we have obtained from the device. Mm-hmm. The reason why it takes like so long is because the tests we have to conduct are really expensive, and it just takes time to get fundings and then to investigate into it. Mm-hmm. After the first flight we are going to have in about 2 weeks, we are planning to dig deeper into Raman spectroscopy, and we want to expand our research in this area. And thanks to it, we will be able to distinguish between the type of pollution we have on the filters.
Yes,
because right now we just know that we have, right now we just know that we have pollution, like we have pollutants there, but we don't really know if it's like we don't know the type of pollution. We don't know if it's just some small particles, is it microplastic or any different thing.
Right, and Eva, there is one more research piece that I think is on our screen right now, actually, and we didn't mention it. Some irradiation measurements of the device. I think, Eva, you can elaborate a bit more on that, but basically we've conducted irradiation measurements to see what radioactive isotopes were gathered on the filters, and I believe we found potassium. Eva, you can elaborate on that a bit more.
Yeah, we didn't find anything dangerous for us as humans. The only thing we found was actually potassium. So it's the same thing found in bananas. So it's nothing dangerous and nothing significant to know.
So the good news is there was nothing dangerously radioactive above Poland at the time we launched the balloons.
Yeah, but because of the small samples, because of the small sample size, we will probably expand our research into it, because I think that we want to actually create some sort of a difference between, for example, concentration of isotopes on different levels, but we need more samples to do it.
Obviously, the amounts of samples, the number of particulars we're working with is trace amounts. We're not working with like, let's say, grams of pollution. We're working with micrograms. We're working with very small amounts of it. So it's trace amounts. And this obviously requires very precise research.
Sure. So quick question to your technical team. How much air are you, because from what I understood from your description, you are processing more air than just what fits in the tube. So what's the volume that you are collecting?
I reckon Philip has information on the turbine performance, so Philip can talk a little bit more about that.
We don't know how much air the turbine can suck into the device, but we are working on the systems that could tell us how much air how much air floats from the filters.
Yeah, that would be extremely useful, because then you could actually calculate how much pollution there is.
Yes, so sure, you would be able to measure the pollution density per, for example, cubic meter of air. As of right now, it's more of a qualitative research than quantitative, but we should be able to. Yes.
Perfect. If there are any questions left, please let me know, and I will have a little bit more time to answer that. If not, just contact this amazing team afterwards, especially if you have any applications for collecting samples.
Yes, so the applications are very broad. Pretty much anywhere that we need samples of anything that's suspended in the air, we can use this. We're working on an extreme environment version, so I reckon pretty much anywhere that anyone wants to gather samples of air or anything suspended in the air, we can use this. For the contact, I believe I'm just going to leave my email for a second here.
Perfect.
Just to make the chat that if anyone wants to contact us, they have something.
You can also type it into the
okay. Yes, will do. Thank you. Right, I'll just drop it in. All right. So if there's any more questions, feel free to ask. And if not, I think I can yield the floor back to the honorable chairperson.
Perfect. Thank you again to everyone that did amazing job today talking about the space explorations mostly. And if you would like to have a coffee or tea or something to eat, now is your chance, because we have a break until the next 30 minutes until the next session. Thank you again very much, and see you in 30 minutes. Bye.
Thank you.